Thanks, Angelica. Welcome to the webinar on fraud analysis using the graph technology and machine learning. I am Nav Mathur, Senior Director of Global Solutions at Neo4j. And Graham, why don't you say hi as well?
Hey everyone, I'm Graham Gansel. I'm the data science lead at Expero. My focus is in deep learning and graph.
Thanks, Graham. And Expero is a wonderful partner of Neo4j, and together I think we can solve a lot of fraud issues. So here we are going through this. So the agenda for today is we'll talk a little bit about the complex world of fraud and who are today's fraudsters. And then we'll talk about how to fight fraud rings with graph technology, how graph technology can really help you to complement your current fraud detection algorithms. And then we'll get into more different types of fraud, like credit card fraud. And you know, we will along the way have a little demo on that as well. And then Graham is going to also talk about how machine learning fits into fraud rings and credit card fraud. And then we'll go through a typical architecture of how all of this comes together to solve an end-to-end fraud problem. And then we'll summarize, and the Q&A will follow. So that's the plan. So talking about today's fraudsters, you know, the world of fraud is no longer simple and static. It's evolving constantly. Fraudsters are no longer individuals. They're now organized in groups of multiple people, then go into tens and hundreds of people that are organized as groups and perpetuating fraud. Have synthetic identities, manufactured identities. And in many cases, these identities are stolen from multiple places and amalgamated together. So it's not just one person's identity just directly used. And they're often on hijacked devices. So the types of fraud, there's of course fraud emanating from credit cards. Merchants can be rogue. There are fraud rings of multiple people working together, colluding to perpetuate the fraud. There's insurance fraud. There's e-commerce fraud. And most importantly, there's fraud that we don't know about yet, and that's really what we're trying to solve here. If you know the fraud patterns, then you can kind of figure that out in different technologies. But if you don't know that fraud is actually occurring, it's hiding among the regular transactions, how do you detect that? So let's talk about that a little bit. Typically, if you look at these data points as regular transactions, you might find some anomalies within those that are discrete anomalies. And by that I mean, there might be an IP address that is, we know, has in the past perpetuated fraud, or there might be two transactions coming in, from the same credit card at the same time. Things that are very discrete in nature that can be caught. These would be the anomalies. But these days, the fraud is more like patterns, and we need to detect these patterns of, where a person is sharing an address with another person, and together they are perpetuating fraud, or multiple people share a common bank account or social security number, and so forth. And that's much harder to detect and catch because the individual transaction appears pretty normal. And so we need to detect that and respond to that in real time. And that's really the name of the game, and doing it fast. And that's where the graph technologies come into play. So in a traditional technology like a relational database, you're looking at pretty much discrete analysis where you're looking at individual elements of fraud. But when you connect the data pieces together and look at patterns, you need something different. You need a graph. The data now looks more like a network. It looks like a graph. And so you need a graph technology that stores the data as a network so that you can detect these patterns very easily. So let's talk a little bit about the Neo4j graph platform to help you understand how this works within the graph platform and what is the secret sauce. The Neo4j graph platform covers both graph transactions or the transaction processing side of things, where it's super fast at detecting patterns in real time. But we also bring the world of analytical processing together, so we can do both transaction processing and analytical processing together in one system. And we surround this database with the typical elements of any graph platform, like data integration, bringing in batch data, bringing in real-time data into the database, having the analytics tooling, the development and administration environment, the visualization on top of it, and of course the APIs and drivers for different languages for you to write the applications in. So it's a comprehensive platform. And what has changed recently from a Neo4j perspective is the addition of the additional features on the analytics side. So we are now able to offer procedures that are pretty wide ranging, that you can write to do the analytics. We have some standard algorithms that you would typically do like in a Spark or a cluster. Now you can do that in Neo4j. More about that on the next slide. And of course, integrating with typical analytical systems like R and Spark and so forth. So we have a pretty well-rounded analytics suite now. So going into the graph algorithms, we can now do standard things like path finding, finding the shortest path, finding centrality, doing community detection. And these are all great techniques to find fraud. So these are all now available directly within the Neo4j environment. From a differentiation perspective, we differentiate with non-native graph databases, other NoSQL databases, and relational databases. So the difference between native and non-native is really that we store the data as a graph right into our storage layer. So every aspect of like going from the whiteboard where you design your schema to the logical model, and there is no sense of a physical model in our system. The logical model is the physical model, and it is stored and visualized as a graph. So our underlying storage technology actually not only stores the data, but also the relationships as first-class citizens. So that is the core differentiation between a native graph platform and a non-native graph platform. The non-native graph platforms use, whatever their core underlying storage is, whether it's a key value pair or a document or other columnar storage. And then on top of that, they have a layer of translation where they then translate that underlying storage back to a graph. And so they suffer in performance, they suffer in the ability to keep the ACID nature of a database, and they frequently lose transactions. So that's the core difference. And of course, from an RDBMS perspective, once you start having 4 or 5 different joins, the performance level degrades very, very rapidly. And so to find patterns that are 20 levels deep is going to be extremely difficult, if not impossible, within a RDBMS. So those are sort of the core differentiation between the different technologies and why graph databases are so suited for pattern recognition. So from an architecture perspective, we have a term called index-free adjacency. What this really refers to is pointer chasing in memory. So we're not looking up indexes when we when we look at these patterns. We look at the relationships, and the relationships are just a pointer away from the current data element to the next data element. And so it's very fast because it's all CPU math. We're not actually doing any index lookups when we go to the next element of the relationship and so forth. I talked about ACID already. We have full stack clustering, and our clusters again maintain that ACID nature of the database across the cluster. We have all the right language drivers and tooling for writing your applications. We have optimizers built in so that your queries can be, you can look at the plan and optimize it. And then, of course, we have hardware optimizations as well. So our footprint on the hardware side is pretty small in comparison to our competition for the kind of throughput and compute power you get with the graph algorithms. So let's get into the different fraud types, and let's talk about fraud rings to start with. Here's a quote from Gartner. I think it's very apt. Don't consider traditional technology adequate to keep up with criminal trends. So I think really what Gartner is pointing to is, look at as the fraud evolves, as the fraudsters evolve the technologies, they are using graph technologies to perpetuate fraud. And you don't need to be stuck in the old world of relational and other technologies to catch them. They are leaps and bounds ahead. So we need to evolve our technology as well to catch them. So again, just to make that point on discrete methods again, discrete methods could be endpoint centric, where you're looking at the endpoints and their IP addresses. You could be looking at the user IDs. You could be looking at transactions and seeing if there is no anomaly with the transaction where the same credit card is being used at the same time from two different points. So these would be all sort of discrete methods of detecting fraud. But the weakness is that fraud these days is normally all within the normal band of things, and the fraudsters have got pretty intelligent to not just use discrete methods or individual fake IP addresses and so forth. They're really trying to coexist with the normal transaction and make it look appear as regular as it can be, but more acting in together as a ring to perpetuate that fraud. So these type of techniques are unable to detect fraud rings and hijacked devices and synthetic identities and so forth. But because these type of fraud rings really form a pattern within the normal behavior, to detect patterns you need cross-channel connected analysis. You need entity linking, which is all essentially points to a graph. So here is an example of a fraud ring as a graph. So you could have three different people, having different credit cards, different bank accounts, and loans and so forth. So they're pretty regular as they appear right now. But then, they could share phone numbers, they could share addresses, they could share social security numbers, and that's where sort of the fraud comes into picture. And to kind of catch this kind of a fraud ring, you need to be able to recognize this pattern of shared phone numbers, shared social security numbers and addresses. And this is a very simple 3-person ring. This could be much larger in nature, and it becomes much harder to find those anomalies in discrete analysis. But with the pattern-based analysis, it becomes much easier. So Graham, do you want to talk about how ML fits into all of this?
Yes, indeed. So we've touched on a couple reasons here why graph is more powerful than sort of relational or tabular-based data, especially for detecting fraud. And I want to touch on the technical aspects of implementing these algorithms with respect to graph. So we have an example on the right-hand side of a highly connected graph that is paired up in rings in a great deal of complicated relationships that form many different rings. And we can't teach a standard deep learning algorithm to tease out the fraudulent cases from the normal cases in this graph because it simply doesn't fit into the framework of standard machine learning techniques. So because this is a technical deep dive, let's dive into some techniques. So on this slide, we actually have a real set of businesses interacting in the graph you see on the right-hand side. Each one of the nodes in this graph is another business entity, and the edges between those entities are financial transactions of some sort. In this case, we've actually grouped series of financial transactions between these companies. So we want to determine whether or not the yellow group of businesses on the lower right-hand side of this graph is in fact a group of standard businesses, or if they're really a money laundering ring. So the way we're going to do that is by building an algorithm which extracts subgraphs from this large graph of businesses based on some metric, which we could say is a edge threshold, or maybe a Louvain community, or we could do some unsupervised learning technique like k-means clustering. And when we've extracted that subgraph, all of the subgraphs rather, we will calculate so-called graph topology metrics for each one of these subgraphs. And I have a list of those on the left-hand side. We won't go through all of them, but these are a small group of topology or geometry metrics that we'll calculate for these subgraphs. So once we've done this, on the next slide, we see the application of a machine learning algorithm using these graph topology networks. So this is a schematic of a deep neural network. In this case, this is a standard multi-layer perceptron with a dropout layer. That's the one with the white holes in it in the middle. And into this deep neural network, we feed for each one of these subgraphs the feature vector we've built out of the graph topology metrics. The feature vector that you see on the left-hand side actually is the graph topology metric measurements that we take for each one of these subgraphs. And in fact, we can connect or concatenate node properties into each one of these feature vectors if we desire. So we could potentially, and I'm not showing this here, we could potentially take averages or some other mean measure of node properties for each one of the subgraphs and concatenate them on to the feature vector on the left-hand side labeled financial ring metrics. All of that information goes into the thing in the center, the deep neural network. And of course, there's a huge variety of architectures you could use there to do that. And the output from this network typically is, in this case, I have the label that says laundering or not laundering. This would be, again, this money laundering ring estimation that we're trying to perform. And you get a confidence back in a log probability or in a probability itself. On the upper right-hand corner of this slide, I've actually included some code to define this network you see in the center of the slide. So you can, if you're familiar with neural networks, you see that this is quite a simple one. It's just a series of connected dense layers with a dropout layer in the middle and with a softmax unit, classification unit at the end. Now, Nav is going to take you back into the world of fraud and talk about credit card fraud.
Thanks, Graham. Actually, before I do that, I wanted to, we did promise a demo, so let me just walk through that. So here is, a quick demo on fraud rings. So this is a simple application, for demo that we built. We've injected some from fraud into normal transactions, and you get over here a sense of how many fraud rings are there in the data, and so on and so forth. So and so let's get into the fraud rings. So here we have a simple two-level fraud ring where these two people share a common phone number and a common social security address. So it's pretty straightforward. But you can very easily get at this information. You could see how quickly that query was performed to actually get all of this data, because now you have this data in a connected fashion already available to you. We can kind of see if there's any other piece of data. So here is the bank that's linked to the to this credit card, and so forth. So you can keep exploring this data in that manner. Here's something more complex. This is a 4-person ring, and you can see the complexity of this and how traditional technologies would not be able to address this very easily. So here you have 4 people sharing a common address, and then within that you have a couple people sharing a phone number and the social security number. Here again, you can kind of see if there's other information that you can glean. Is there anybody else using this phone number? No. You can get the bank account. You can, double click on any of these things and get more information. So that's kind of a view of how fraud rings can be detected within a large data set very easily using Cipher and graph technology. And then let's see. Here we get into phone transactions. So we have a few of them here as well. So we have 2 people using the same phone number, but actually there are more. So let's see, there is people doing money transfers with that phone number here, and so you can start exploring the data like that, and you can pretty soon understand that this phone number is sort of central to the fraud that is being perpetuated by multiple people, not just these 2, but this person here may also be linked to that fraud, and so on. And you can keep exploring this and expanding this. And these can form even larger patterns where you see multiple groups funneling money into a single bank account, over several hops. And so that becomes, again, very difficult to detect with traditional technologies. But with a graph, you can see the relationships, and you can see where all the data is pointing to. And traversing that and getting to that very quickly becomes quite easy with the graph technology. So that's a demo. Unfortunately, Graham had a demo as well on the machine learning, but due to some technology limitations on showing Linux here with the GoToWebinar, we were not able to actually do that. So back to the presentation. Just a second. And we will talk about credit card fraud here next. So here are a couple examples of credit card fraud. The first one refers to credit card testing. So here what happens is the fraudster gets hold of a skimmed credit card through a rogue merchant or through a skimmer at an ATM or through a data breach. These guys actually get a lot of cards through data breaches these days, and that's become very common. So once the fraudster has got a credit card, the first part of this on top really is normal transactions that the cardholder does at different merchants, so several transactions that you can see there over a period of time. But once the fraudster has a hold of this person's credit card, they actually try to mimic these normal transactions, and that's what is called the testing activity. So they're doing small tests like $2, $5, $10. So they could be going to a Starbucks and buying a cup of coffee. They could be going to a McDonald's, getting a value meal or whatever. These are very common merchants at which this type of fraud is perpetuated, and this is called credit card testing. So what they're doing is they're really testing the card at incremental dollar amounts to make sure that the card doesn't trip up any alerts or any alarms. And once they're reasonably sure after 3 or 4 tries, they make that big, large purchase of their favorite thing, whether it's a piece of jewelry or a computer or what have you. And that's the fraud that we're really trying to prevent. So this then really forms a pattern of tests, which is 3 or 4 tests of increasing dollar amounts that then leads to a very large purchase. So if we can detect that pattern, in a sea of transactions in real time, we can prevent this large transaction from going through. The other example is on fraud origination and assessing loss magnitude. And this example really is an extension of that credit card testing example. So if you look at John, he has a bunch of transactions on his credit card. They all appear normal, but when John detects this $2,000 charge at this computer store, he realizes that this is not something that he has done, and he reports that fraud. And so the credit card company then goes back and looks at all his transactions, and sure enough, they find that credit card testing kind of pattern right there, and which originated at a gas station some time back. So now they suspect that there might be other people because that are also be defrauded at this gas station as well. So this might be a point where the credit card got skimmed. So then they start looking at other transactions at this gas station within that period of time. Maybe it's 4 hours or a day, or within the time John's card was stolen. So they find Sheila again with the same kind of testing transactions, and then they find the big purchase there, the jewelry store. But Sheila never noticed it because she never really looks at her, credit card statements. So they were able to find that fraud. And Robert also went to the gas station, but he got lucky. His card was not stolen. So you always have that. And then you have Karen, which again, was prey to the skimming of the credit card. So the bank is now basically not only walking backwards from this $2,000 transaction at a computer store, they walk it all the way back. Then they find a pattern within that gas station, and then walk each person's transactions forward to assess the complete loss magnitude due to that particular fraud. And this is a pretty complex pattern if you think about it. It goes into hundreds and hundreds of transactions, and doing that with any kind of regular technology is going to be literally impossible. This is really where the graph technology shines through. Over to you, Graham, for the next bit of this.
So again, let's take another deep dive and look at how this is actually done in practice. I have a note on here about $118 billion lost each year to false positive fraud detection. This is when you go to a gas station and try to make a purchase, and then directly after that, maybe you do go to the computer store Nav mentioned and try to purchase a new MacBook, and your card is declined. And you say, I have to call the credit card company and get your card reinstated, right? So that credit card company potentially just lost $2,000 worth of business on your new computer purchase. So we want to both increase the accuracy of our fraud detection abilities and decrease the false positives that our algorithms generate. So that would be called the reactive case, right? So Scott and Amy in the first webinar in this series talked about fraud analysis for both individual and organizational entities. So an organizational entity is related to the fraud rings we mentioned above, but we want to dive deeper onto this sort of individual entity fraudulent transaction scenario. So on the right-hand side of this slide, I have a big blob of graph that is a supernode graph, which means that each one of those nodes represents one entity. Maybe that's one account holder. And we've extracted from that supernode graph on the right-hand side in the gray box a single individual, and we are looking at each one of their transactions there in that star-looking subgraph. So once we have that information, on the next slide, we'll show a situation of applying a certain type of embedding to that subgraph. So now we can see the next slide. And here we have on the left-hand side a little three-dimensional rendering of one of these individual purchase subgraphs. And on the right-hand side, we've collapsed that information into a two-dimensional so-called embedding space. So this can be done in a variety of ways. And in fact, I'm showing two ways here. The blue information on the right-hand side represents a principal component analysis. And the orange methodology is called eigenvalue decomposition, or in graph terminology, sometimes it's called spectral embeddings. So we can collapse this information into as many dimensions as we like. And it's necessary to do that to input this information into the architectures shown on the next slide, where we have two different varieties of, again, deep neural networks, which look at these embedded graph spaces to, again, output a confidence or probability that transactions or groups of transactions are fraudulent or not fraudulent. So on the upper section of this slide, we have a deep convolutional neural network. This looks at a group of transactional information in this embedded graph space to make a prediction about fraud or not fraud. On the bottom of the slide, we have an architecture similar to, but not identical to, the architecture we discussed before, which is a pretty straightforward deep neural network. This again is a multi-layer perceptron, in which case the first step is to take that embedded graph information, credit card information in this case, and flatten it into a feature vector. And we can do that in one of two ways. One is we can do our standard data science techniques of chopping data at set thresholds and stacking them together, or we can actually do this when we do the embedding. Instead of embedding into two dimensions, we would simply embed into one dimension. On the right-hand side of this slide, we have more code for your review if you're into that type of thing. The upper section of code is how you would implement that top deep convolutional neural network architecture. And the bottom is a different implementation of a deep neural network in this linear setting that we discussed before, but in this case, we have a different network architecture without that dropout layer. So now that we've discussed both individual and organizational fraud settings and analysis using machine learning, on the next slide, we're going to dive into a superset of this analysis. So we want to build a system that's capable of analyzing both types of fraud while utilizing the true graph structure and the node property information simultaneously. So we have a picture on the right. This again is a financial transaction graph. It's a subgraph of a much larger bank data set where we have colors representing merchant or individual financial transactions. Again, the edges are those transactions. I have a note here in the second bullet point before we move on that this architecture I'm about to discuss is a true production level fraud analysis neural network architecture. So it's a bit more sophisticated than the types we've talked about so far, and it's a bit more complicated to implement in terms of computational power and resources. So keep that in mind while we go through this, and I'll try not to bore you with too many details. Our next slide here is a diagram, another schematic of this so-called graph convolutional neural network. So we talked about convolutional neural networks already as they apply to fraud analysis. And now we'll add another layer on top, which is a graph convolutional layer inside of that architecture. The reason we want to do this is so that instead of applying those embeddings we talked about before, which actually are applicable in many cases, we insert the entire graph into this graph convolutional network. So the full slide is a schematic of this thing. At the output, where you have class on the right-hand side, again, is a fraud, not fraud confidence prediction for each one of these entities. And again, I've shown code about how to implement this graph convolutional neural network layer on the bottom right-hand side. So if you're interested in that, you can review it when after this webinar is over. It will be hosted, and you can go review it. So the next slide has a representation. Again, this is a question we would ask in a production setting. Is this highlighted business in this graph committing fraud? Well, if we click over one more slide, we'll see that in fact, it depends on where the money's going. So we have to analyze all of the transactional information relating to the potentially fraudulent transactions to make a safe and confident prediction whether these things are fraud or not. So unfortunately, you didn't get out of this webinar without seeing some math. On the upper right-hand side, I've shown the equation, which is implemented in the code I showed on the previous slide. But that's how you actually implement this workflow. And again, there's the architectural diagram on the lower left. So this is the same architecture. And in this case, instead of classifying node properties, we'll be classifying subgraph properties. And we do that by building this company supernode graph. If you click the button one more time, we will see how to build that graph, that supernode graph. All we do is collapse down these communities into a single supernode connected by their financial transactions. So again, this is a graph that we saw much earlier in the presentation, and we're doing a different type of analysis to detect whether this group of businesses is committing perhaps money laundering types of fraud. And again, I've shown that equation here. This is, once again, that graph convolutional neural network architecture. So it's a flexible architecture, and it is an architecture which is applicable in a wide range of settings and a wide range of production settings. So it's very nice to use it. So I'll hand it back over to Nav, and he can tell you how this actually all fits together in a production setting.
Great, Graham. Thanks. So we actually already did the demo. Like I said, this was the placeholder for Graham's demo, but we are not able to do that today. So sorry about that. But how does this all fit in? By the way, I just wanted to highlight a point that Graham made on the false positives. Do you know that the false positives are 13 times the actual fraud that that gets committed? So that's a huge number, and that's why a lot of financial services firms uh, tend to be on the side of not caring about fraud so much because they're really worried about the false positives and the loss of revenue because of the false positives. Interesting story. Once I, was in my hotel room late at night trying to book a very expensive flight, and just because I'd just gone to this new place, my card, large dollar value transaction, new location, got denied. And since it was late at night, I called the credit card company, and they were not able to do anything about it because their fraud department was gone to bed. And so I had to really use a different card to make that transaction. So they lost money on this. And this is a real scenario every day of the week for banks, and they're really worried about that. But I think with this kind of pattern analysis and machine learning, as Graham showed you, detecting these false positives with a high degree of certainty with a score-based approach really makes a huge difference. So anyways, here is kind of an overall end-to-end architecture for fraud. So you typically have a lot of these transactions from your mobile devices, your all the different purchases that you're making, the transactions you're doing at the bank. They're coming in at your bank into some kind of a relational database, and then you have basically your data science team that then takes those transactions and then couples that with the merchant data that you're getting from the merchants, the credit score data from the credit rating agencies, other third-party data. This is all sort of being fed into typically a data lake at the bank, and the data science team is looking to find these fraudulent patterns within this data lake. But again, you don't have a holistic view. You're not able to visualize these patterns in a data lake. It takes weeks and months to kind of really get to the pattern, and then it takes even longer to operationalize that pattern, because now that you've found a pattern, you need to now take it to your enterprise architect or to your solution architect, who then will operationalize that pattern in some other disconnected system that's feeding the ultimate application to detect and prevent fraud. So because it takes so much time, by this time the fraudsters have moved on to the next technique and the next technique. You're really chasing them and not really able to prevent the fraud. You might be able to detect it after the fact. So instead of trying to do this, I think you can leverage a graph technology in this fashion. You can essentially, once you've found the pattern that you're looking for, and you can load the parameters associated with that pattern. So for example, if your data lake has 200 different parameters or attributes associated with the transaction in the data lake, you might only be looking at 50 of those for that particular pattern. You can load data relevant to those 50 patterns into Neo4j. So loading the relevant data, and then you can find all instances of that pattern. You can visualize that pattern within Neo4j, and you can then apply the machine learning techniques to further refine those patterns and remove the false positives, as Graham showed. And once you've done that, and now you've updated, so the database at the bottom I'm showing, that's more the analytics of it, and where you would apply the machine learning, and then you would update back your transactional database. At this point, you have a really strong patterns that you're very confident about, with a high degree of score, and now you can start actually sending the transactions, the relevant parameters of the transactions, directly into Neo4j, so that it can sense the pattern in real time, and it can respond in real time. So it can throw up an alert when it recognizes a fraudulent pattern. It can kick off a process. It can visualize that. So all of that is now possible. So this is a sense and respond type of architecture for fraud prevention, not just detection, but you can actually prevent fraud in real time with this type of an architecture. And because of the machine learning involved, it's the self-learning. So as these patterns are morphing over time, they morph ever so slightly. It might add another parameter, or the values in the range might be different. The machine learning will be able to detect that and rectify the patterns as well. So you're constantly ahead of the game. So Neo4j is being used for this type of fraud detection, in a lot of Fortune 100 finance companies, the government, and also for online retail. It's helping to reduce fraud. It's helping to do better credit risk analysis for loans outstanding. So you can kind of actually look at a loan and its risk profile, not just locally, but because of the connected nature of data you have, you might also look at how this loan relates to not just the company that's trying to fund the loan, but also companies that are related to this company, and how that might even add to the risk profile of this loan. So that's a different level of connected analysis that you can do on such loans, and have a better view of the credit risk that you are getting into as a bank. Of course, reducing chargebacks and adapting to new methods of fraud, as I mentioned earlier. So we have a lot of customers in this area. The government institutions I can't really name, and a lot of the financial services companies as well want to keep this under wraps. But we do work with global companies like UBS. In Latin America, we have Itaú Unibanco, and so forth. So we are a pretty big player in this area from a graph database standpoint. So Graham, you want to talk a little bit about how Neo4j and Expero work together for fraud?
Yes, indeed. So we have a little schematic here of graph and analytics services. So actually on the next slide, we have a workflow of Expero's engagement in the technology lifecycle. We engage across every one of these pieces using Neo's technology in the back end to perform our analytics tasks. So using Neo's graph database, we're able to not only implement back-end solutions, but also do insight generation through data analytics, and we even go all the way through UI. We have an expert UX team here in-house.
Excellent, thank you. And here's actually another slide. I don't know if you wanted to talk about it.
That's right, yeah, so this is our sort of rapid prototyping process. We have a very fast turnaround. We aim for weeks, not months or years, on actual software that's operating in your business. So 4 to 6 week target, depending on what type of analytics you want performed, delivered right to your door.
Excellent. So And of course, as Graham mentioned, visualization is a key part of it. Being able to visualize these fraud patterns makes you really able to fine tune it. Um, you know, uh, the full stack is available between Expero and Neo4j. So if you have a fraud project in flight or under plan, please do contact us and see how we can help you. Um, and thanks for attending this webinar. This is part of a three-part series. As Angelica mentioned, the first one was on business impact. So if you haven't seen that yet, please do check your email. It's also available on Neo4j's YouTube channel. It covers the business impact of fraud. And the next one is going to be about funding. So if you like this, how do you convince your management to fund this type of project? Our colleagues are going to be talking about that in the next webinar on February 20th. So be sure to attend that one as well. Thank you from both me and Graham. And you could contact us. Our emails are in here. And we'll be happy to connect with you and talk further about your initiative. Questions?
Yeah, thank you so much, Nav and Graham. That was fantastic. So we do have a little bit of time left over for a few questions. So again, I invite you, if you do have any questions, just type them into your questions box on your GoToWebinar control panel, and I'll read a few out for us now. So we do have a question around just in general, are there other business areas besides finance where you're seeing fraud detection to be advantageous or being applied?
Yeah, I think it's a good question. Yeah, go ahead, Graham.
Sure, I'll take that one. We have actually performed this analysis in the insurance space as well. It doesn't, in terms of machine learning and graph implementations, this is sort of a domain agnostic procedure, right? We can do this in any domain as long as you have data which is representative of the examples of fraud you're trying to typify. We can certainly do this. So again, we've done this in the insurance space as well.
Yeah, and retail is another big example for us. That there's a lot of retail fraud, especially around promotions, so we get into that as well a lot. We have 7 out of the 10 top retailers are our customers. So yeah, that's another big area for us. And like I said, government and intelligence. It's a different kind of fraud. It's more intelligence, but and piecing together intelligence from multiple sources to actually get a better understanding of what is going on.
Great. And perhaps a question for Graham. What is the platform that you're performing deep learning on?
Again, we're platform agnostic. We can do whatever you want. I sneakily inserted code in I think 4 different platforms. So I showed 3 or 4 different code snippets. Each one was written in a different library. So I showed code in TensorFlow, PyTorch, Torch itself, and I believe I also had one in scikit-learn. So we do a lot in Python. Doesn't have to be Python. Again, whatever the client prefers.
Okay, that's great. And for Nav, can you elaborate a little bit about the possibility of using Neo4j alongside a relational database or other NoSQL databases? So basically, is it possible to have a polyglot environment with Neo4j?
That's actually a very common way to do it, because we're not trying to uproot your existing systems, right? I mean, this is a layer that works in conjunction with your existing system. So polyglot architecture is very much some of our clients use that. So we connect up with the existing systems, whether they're key value pairs, columnar, or document, or what have you. And then we bring the data silos together within Neo4j to be able to do this detection and prevention.
Great. And are either of you able to elaborate on some popular techniques to extract subgraphs?
You want me to take that one?
Sure.
Sure. Okay. So subgraph extraction is an art form, and it can range from very, very simple to very complicated. An example of a really simple implementation is using an edge count threshold. So if we make the assumption that within community clusters, what this subgraph we're interested in, these subgraphs we're interested in, we assume that the connectedness is high, the edge count would be very high inside of those clusters. And correspondingly, the edge count between those clusters would be very low. So we could calculate the so-called degree of each node and build a threshold, say if edges are less than 4, count that as not in the same group. So that's a very, very simple example. And we can move into really complicated, sophisticated implementations. Like I mentioned before, we could use unsupervised learning techniques to do this for us. And then we can use the standard graph deterministic algorithms to also perform these community detection scenarios, like, for instance, blue vein community detection.
Okay, great. And are you able to elaborate a bit on any size limits for graphs? Are there really any limits to the amount of data that you can process or import?
Well, I think that it's really the limit is based on the memory that you have and the size of the machine. It's the graph platform, the graph database itself we've got implementations of multiple billions of nodes and edges. So there's no limit as such from that perspective. And also, we're never really working on an entire graph for most part. We're only working on subgraphs and diving into part of a graph and then fanning out from there. So it's, from a performance standpoint, it's not an issue because we're never scanning a whole graph. That would be not an appropriate use of the technology.